Okay, hello everybody. Let's jump right into it. We're going to be studying the rotation of rigid bodies right now, chapter 9, and we'll just dive straight into it. So what we need to do is we need to develop a system of rotational kinematics. So we're basically going back to the basics here. We're going ahead and saying, okay, well, we studied kinematics in translationally, but now we have to study kinematics rotationally. So we have to convert our x, v, and a variables into rotational terms of theta, omega, and alpha. So this is going to be your rotational displacement, your rotational velocity, or your angular velocity, as we like to say, and your angular acceleration. So we like to say angular displacement, velocity, acceleration. You can also say rotational, but the true terms are angular. So in this case, we're going to go ahead and we're just going to talk about how we get from distance to angular displacement. So we do that via the formula of theta is going to be equal to S over R. And we haven't seen S that much in previous chapters, but S is going to be our arc length. And R is going to be our radius of our circle. So if we're talking about a circle here, and we have our center here, this is going to be our radius R, and we divide some length of this circle, like this length here, and we divide that by the radius, we get theta, which is going to be our displacement in here. So this is how we convert from a distance or an arc length to an angular displacement. And so one big conversion factor that we have that you're going to need to know is what a radian is. And radian is our unit of how we is another way of describing an angle. Say you can say. So usually we're accustomed to using degrees, but we can also use radians. And so this is why you have to be careful about which mode your calculator is in. So because they'll do the calculations differently based on whether you're using radians as your units or degrees as your units. So 1 radian is going to be 360 degrees, or the entire circle over 2 pi. This is your conversion factor. So this is basically equal to 1. And so if you divide these two, you're going to get a total of 57.3 degrees, which is basically 1 radian. So 2 pi radians is going to be your entire circle. But 1 radian itself is going to be about 57.3 degrees. So now let's move on to angular velocity. So in the same way that we can take the time derivative of position to determine an object's velocity, we can also take the time derivative of our angular displacement to find our angular velocity. So those are one and the same. So all we need to do in order to find omega is to take the time derivative of theta, and that will yield your answer. But you can also do this algebraically as well. If you're given 2 different angular displacements and you divide it by the time interval, that will also yield the same answer. So in order to get this answer, this result, what we can do is all we have to do is take the limit as t approaches 0 of delta omega over delta t. Basically, that's all we need to do, is we just have to take that limit. Or take the limit as this is omega. Or this is theta. We could do the same thing to find our angular acceleration later. So, same thing goes for angular acceleration, and that will give us d omega over dt. is going to be equal to the limit as t approaches 0 of delta omega over delta t. So there we go. Okay. Now we've correctly written out those limits. So in this case, we can go ahead and we can go ahead and derive all these formulas pretty easily, but I feel like doing those derivations is going to be redundant, as if we just go ahead and we compare our kinematic equations from our second chapter, we can just go ahead and see these. So if we say, I'm going to give you this chart that's going to be out of your book. This should be table 1.9. So if we have AX is equal a constant and alpha is a constant, we're going to say this is going to be AZ, this is the angular acceleration around this z-axis, is going to be a constant. And we can then say that Vx here is going to be V naught x plus AXT, and we can say that omega z is going to be omega naught z plus alpha zt, and the same thing goes for these kinematic equations here. We have x is equal to x naught plus v naught xt plus 1/2 ax t squared. Because in this case, we'll get theta is equal to theta naught plus omega 0 or naught z t plus 1/2 az t squared. Then the list goes on for the rest of the kinematic equations as well, and I'll write them here for you. So as you can see here, this comparison is going to be vastly apparent at this point, that these equations are going to be very comparable, and you just merely have to convert from one to another. I'm just changing colors here real quick. My ink's running out. Okay, so now we've gone through and detailed all of our kinematic equations for fixed axis rotation and constant angular acceleration as a comparison with our straight line motion with constant linear acceleration. So you can see that these two sets of equations are going to be equivalent to each other, barring a conversion from one to the other. So what we can do is we can start to detail some of the relationships that we have used before in some basic conversions. So we went ahead and we said that there's a conversion, but what is it actually? So from before, we said that that S is equal to R theta, and we can also say that V is equal to R omega, and that A is going to be equal to R alpha. These are going to be our three conversions from one to the other. And we can write R alpha in a couple different ways as well. So we can also say that, remember that A radial was equal to V squared over R. Well, we can put in what V is supposed to be equal to, right? And so then that's going to yield that this is going to be omega squared R. Because we have an R squared and an omega squared on top, one of those R's is going to cancel with the R on the bottom, and this is what you're going to be left with down here. Okay, so next up, we're going to talk about some. We're going to move on very quickly from kinematics because we've detailed how these kinematic problems work rotationally. So you just have to use these sets of equations instead of these sets of equations. So they're the same. They're going to be very similar problems, but we're going to have to move on and talk about energy now that we've talked about kinematics and some of the conversions between the two. So if we want to talk about kinetic energy inside of rotational motion, we have to take our equation for kinetic energy, where K was equal to 1/2 mv squared, and we know that V is going to be equal to R omega. Then we have to replace this now and say that this is equal to 1/2 m R squared omega squared by inserting V in here. And so this is going to be for a single object. Now there can be more than one object in a rotational system here. So we're going to have to detail this with i's, and we're going to have to eventually convert this into a sum. So K total, or KT, is going to be equal to the sum from I to N of 1/2 mi Ri squared omega I squared. And so one thing that we can do very, very quickly is, or that it's going to want us to do very, very quickly, is they're going to want us to factor out an omega here. And this is actually not going to be I. So we don't actually have to sum over omega here. And so then, now this equation, we can easily factor out a 1/2 omega squared, and we are left inside the summation with mi Ri squared. And so this quantity here is going to be our moment of inertia. And we're going to detail that with the variable I. Or we're going to denote it with the letter I, or the capital letter I. And so then for kinetic energy in a rotational system, we can say that K is going to be equal to 1/2 I omega squared. Let's be clear that this is not a new form of energy. It's simply a sum of the kinetic energies of the individual particles that make up this rotating rigid body. So you can do that. You can use this theorem to go through lots of different problems with several point masses located at different points, and you'll be able to go ahead and use this to solve your problems. One thing that you guys are going to have to learn, because I don't know if all of these formulas are going to be on the test when you're talking about rotational motion, is the table of moments of inertia of various bodies. This should be table 9.2. This is a very, very crucial table. I'm looking at it now. So what you're going to want to do is you're going to want to memorize the formulas for the moments of inertia for various bodies. So these include slender rod access through the center. So what this means is that you have you have a rod, right? And the axis of rotation of which this spins is going to be in the center. So in this case, the moment of inertia of the rod would be I is equal to 1/12 ml squared. But if we were to shift this axis and we were to take this rod about one of its ends, we would be able to say that I is equal to 1/3 ml squared. And basically, the moment of inertia is a measure of how hard it is to make an object rotate. So it's basically, in terms of a rotational motion, a measure of a mass and how hard it is for this object to rotate around a certain point. So for a lower moment of an inertia, it's going to be easier to rotate the object than if it was. So it's going to be easier to rotate this rod like this than it would be to rotate this rod like this. Okay, so I would go ahead and study table 9.2, the moments of inertia of various bodies. Those are going to be very, very useful on tests and whatnot. And so we're gonna wanna extend this extend a couple other theorems here before we end this chapter. Okay, class. So next thing that we're going to discuss is the parallel axis theorem. So what we're going to do is we're going to define this theorem first, and I'll give you the formula right up front. And so we have IP is going to be equal to ICM plus MD squared. So this is when you have two objects, or you have two or more objects, and you have to find the overall moment of inertia of these two objects together. So in order to use this, we first have to define what ICM is going to be. So let's do that first. So ICM, let's get a better marker. ICM is going to be sigma mi xi squared plus yi squared. And so what we're doing is we're writing this expression for the moment IP about the axis through a point P. And we're letting mi be a mass element in our slice with the coordinates x, y, z. Then the moment of inertia, ICM of the slice about the axis, is this. And so what we can do now is we can also say that now we have that IP is going to be equal to ICM here. So I'll plug that in there. And then we have to take into account the other part here, MD squared. Okay, so I think drawing a diagram is going to help with this. So let's get our coordinate axes here, like this. This is our origin here. And this is going to be also our center of mass, CM. And let's draw a line out here to this point P. And so this is going to be a distance B here, and this will be our distance A. And so this distance here is going to be our D here. And then further out, we'll have this here is going to be MI. And we'll denote this distance here, XI. So then this distance here is going to be XI minus B. And then this distance here is going to be YI minus A, this distance in between here. And so this is going to be MI, so we can put some dotted lines here. Should be there. Okay, so we've got mostly everything denoted here. And so now we can write a couple expressions about IP. So then IP is just going to be equal to sigma is equal to MI, and then we'll be able to combine the two expressions into XI minus A squared plus YI minus B squared. And this will give us our formula, because what we've done is we've expanded D here, and because D is equal to X squared plus Y squared. And so then from here, we'll be able to use this to form these coordinates here, or to form this formulation here. A good example of the parallel axis theorem is, say you have a platform, right? And on this platform, you go ahead and you can sit crisscross on it. And say you have a 45-pound plate that you're holding in. So when you're sitting on said platform here, and you have your weight close in on your person here, this is the weight that he's holding, then let's make this platform a little smaller. When you have the platform here and you're spinning, all the weight is pulled in close. So you're going to end up spinning faster. And then when you hold the weight out, you're going to be it's going to be harder for you to spin, so you slow down. This is also shown quite brilliantly by ice skaters. So if you guys have ever watched the Winter Olympics, whenever an ice skater pulls their arms in, you can see them spin faster and faster and faster. That's because they're using physics and moment of inertia in order to get more revolutions per second and increasing their angular velocity while they're spinning. Another thing that comes quite apparent when you're using this example, so say the person then holds out the weight. If I can get this marker to work. Say this person holds out this weight, right? Further away from them. Then this here is going to be our distance D, and this distance D is going to increase, and therefore their moment of inertia using the parallel axis theorem is going to increase. This is D. So as D goes up, moment of inertia also increases as well, while the original ICM stays constant. Okay, so next up, we can use this parallel axis theorem with small mass elements, right? Not small mass elements, but distinct mass elements. Well, there are going to be certain calculations where you have continuous elements, such as a solid object. So for solid objects like this, we can say that I is going to be the integral of r squared dm. And so one thing that we can do with dm is we see that m is going to be equal to rho times the volume, right? And then when we take the derivative, right, the density is going to be of a continuous object is usually going to be continuous. So one assumption that we're making here is that the density is going to be a constant here. So when we take the derivative dm of the mass, the change in the mass, it becomes with respect to the change in volume here. And so then we can rewrite our integral as r squared rho dv, where in this case dv is going to be equal to, in a circular standpoint, if we're talking about a spherical object, dv is going to be equal to dx dy dz. And so what we can do is, for some cases, well, actually this would be not a spherical case, but it would be more of a box type of deal, more of a cube. There's the okay. So we can just do a couple things to simplify this integral. All we can do really is take out rho, because we know it's a constant, and this is what we are going to be left with. So what we're going to do now is I'm going to do an example out of the book. This is going to be example 9.10 from the 13th edition of your book. And so in this case, dm is not going to just be is going to be dv, right? But from here, we're working with a cylindrical shell. So in this case, we're going to have to work with the volume of that cylindrical shell. So in this case, dv is going to be equal to, we're going to have dv is equal to 2 pi r L dr. And so then we can plug this into our integral. And so what we're going to end up getting is we're going to get r squared from r1 to r2. And we'll have rho and then 2 pi r L dr. So we can take all of our constants out of this integral, so we can evaluate it. So we'll have 2 pi will come out, rho will come out, and so will L. And so then from here, we're going to get that we'll have this integral here, r cubed dr from r1 to r2. And so very quickly we can evaluate that integral. We'll have r4 over 4, and from there we'll have to evaluate it from r2 to r1. And so then this is going to be 1/4 of r2 minus r1. These will be to the 4th power here. And so then very quickly, what we can do is we will be able to factor this quantity here. But let's first write down the result of our integral. So we're going to have the 1/4 is going to cancel with the 2, leaving us with a 1/2 here. So we're going to have pi rho L over 2 times r2 to the 4th minus r1 to the 4th. and this is going to be the difference of two fourth powers, I guess. And so we'll be able to factor this very easily. And so from here, what we'll be able to do is we will be able to say that this is going to be equal to R2 squared minus R1 squared times the quantity R2 squared plus R1 squared. And then, yeah, we're just using, this is going to be the difference of two squares, but in this case, we're going to have that A is equal to R2 squared and B is going to be equal to R1 squared. And so we have to, what we're going to do is we're going to express this in terms of the total mass of the body. And so then in this case then we're going to have that, that V here is going to be equal to pi L R2 squared minus R1 squared. And so from there we can replace some of the parts of our result with the actual volume itself of the cylinder. And we can also write that its mass, M, is going to be equal to rho times V, which then gives us rho pi L R2 squared minus R1 squared. And so then we can start to rewrite our moment of inertia I in terms of our total mass and volume. And so from here we can put in what our mass is going to be, or what our volume is going to be, and so we can factor that that guy out. And so then we have that this is going to be 1/2 M R2 squared plus R1 squared. And so if we were to evaluate certain cases for this, we can do a couple things. We can say that for say the cylinder wall is very thin, that would mean that these R2s are basically equivalent to each other. And so then for say a hollow cylinder, we'll call this a hollow cylinder, then these two are going to be equal to each other. And so then in this case for hollow cylinder, we can say that that I is going to be equal to M R squared. And then for the case where the cylinder is going to be solid, then we can say that R1 is going to be equal to 0, and we'll say that R2 is equal to R. So for a solid cylinder, we have that I is equal to 1/2 M R squared.